rolling. Is it rolling? Yep, sure is. That's how time goes. Where's everybody? Is that it? What do you guys think?
Anna's definitely here, but there's a line for like washing hands. So yeah.
You guys have to wash your hands first before you
Yeah,
come
just
in.
wash your hands before you come in.
Guten Morgen.
I think Aaron's in there. Sorry.
Nee. Oder?
Hast du nichts mitgebracht?
Doch, schon. Also
Deinen alten Apfel?
ich habe zwei Böcke.
Hey, yeah, I was going there.
Good morning, Anna.
I have a handout for you. Actual physical handout.
That's fancy.
Thank you. I think it's very fancy.
I don't have mine paper, I know that.
Well, I figured I'd bring at least one piece of paper in case somebody doesn't give you right at that back, I guess.
No, I don't have paper. Sure. This is every week something, right?
What? Lars is
Yeah, Lars is right.
Is Lars coming?
yeah,
Lars should be
last
coming.
person.
Should be.
Lars
Alright.
should
Yeah,
be.
Aaron, good job.
What am I supposed to write? Like,
What's
I
that?
have my lock.
Yeah.
What am I supposed to write on
I think you write your name on it, and yeah, each student should write their name, class, and lock combination on the tag.
it? Okay.
And rubber band and tag, each student should write their name, class, and lock combination. Thread the rubber band through the tag and then back through the rubber band. Hang on.
Yeah, Lars is only on this end.
Right, name, class, and lock combination. Then it goes in the box, and then you get it back. Well, then fall, assuming you ever come
Yeah,
back
but
to
I
school.
don't have to write down my lock.
No, because you're getting it. I believe. So, who's next?
Lars!
Lars!
Hi, Lars.
Hallo. Good morning.
Welcome to semi or 1/3 of the class. We're gonna do actual, I know. Like this, the better. Are you just gonna watch the screen
Now you're cut
instead
off.
of watching me?
We see you like
Do you have to duck?
from here, yeah.
Wait, seriously?
Yeah. Well, she
Just hold up, move it up.
Can you move it up a little bit? Just adjust it? Just bend, yeah. How now? Is that good?
That's better.
A bit better?
Yeah.
Can you see me now? Can you see me now?
Yeah.
Okay, good. Cool.
Perfect.
Okay, cool. So who wants to go next for this? So we gotta do the locker thing. We're also gonna do a little learning, which is like actually pretty cool. And I do have a handout. Voila. There you go. And so why don't we just go like up the sequence or something like that? Does that sound pretty good? Okay, so maybe Lena go. Okay, and you do your locker thing and get your stuff. And
How do I tie this together? Aaron, should you go up, backward, like back over the desk?
I need to take that with me then because I'm in charge of an idea. I think. Yes, I do have to take that with me. Oh yeah, here.
Or should I take it back?
Do we have this one Tana?
Here.
Do we have this one Tana?
There you go.
Who do we have next?
Okay, listen up. So I know they're asking us to do like some checking in and all that stuff. I feel like we've checked in, even though this is the first time we're seeing each other in person for 2 months. Do you feel checked in? Do you feel the need to emotionally exchange about the situation, talk about my blue gloves, that kind of thing? This is mostly about reminding myself not to touch my face. That's really what this is about. It's not really about I'm afraid that you guys are going to affect me. But it helps me kind of not touch my face. Is that weird? Okay. Okay. So other kind of emotional kind of check-ins, awkward, super fantastic. That's what I thought. I mean, we've seen each other a lot online, I think, right? So I feel like we have connection. It's not like the first time I'm seeing you guys or the first time you're seeing me. I did give you guys a handout, and I do want to talk about exactly this because this is one of the most important graphs in the history of science. That was my dramatic voice. Was that dramatic?
Yes.
Thank you very much. Thank you very much. So it has some interesting stuff on here, and I want to talk about that. Okay? Now, if you look at the graph, there are two axes. It says average binding energy per nucleon, which you don't know what that is, and on the horizontal axis it says atomic mass number. Okay. Now, atomic mass number, you guys actually know what that is, right? That's something that I've told you is something we really don't want to use. But that's okay, because this graph is prepared by chemists, right? So we talked about this reaction. Are we on screen there, Lars?
The board is.
Yeah, it's good. That's the most important thing. So good. So hydrogen reacting to helium, we did that last time, right?
Yeah.
Yeah, so that good. Okay, so and we had two numbers on here and a number on two numbers on there. What are the two numbers that go on here?
1 and 1.
1 and 1. Okay, exactly. And over here we have two numbers. What are the two numbers over there?
2 and 2.
Two,
No, 2 and 1.
2 and 4 is right. It's cool. This is cool. Yeah? You guys remember this? I'm gonna pretend you did.
Should we take those?
I think that'd be good. That'd be a really good idea. Yeah. In general, yeah, notes are good. Help you learn. Cool. Okay, so down here we have a number. And what's that number down here? Hydrogen 1.
A proton number.
That's the proton number, exactly. We've actually said we're going to rename this number, okay? Proton number. What's the number that normally is used? Sorry, we can actually use charge number. But then, yeah, it's the number of protons, but we want to use charge number for that. But in general, chemists use what name for that? They just call it atomic number. They just call it atomic number. And that's okay in general, but because in chemistry they use atomic number because they don't talk about things like electrons with the same notation. Is that okay, Buffy?
Yeah.
Okay, cool. So, electrons, we'll label that like this. And of course, that's not its atomic number, because electrons are not atoms, right? Right? So that's why we're going to generalize that to charge number for that bottom number, okay? Now, the top number also has a name, and again, our name is going to be different from what chemists use. What's the name we use for the top one here? Is there- Nucleon number. Oh, cool. Very cool. So this is the nucleon number over here. Oh, I'm gonna go. Oh yeah, color. That's a good idea. So we can do like circle these in black. Oh yes, that's a good idea. Yes. Color's so good. So here we go. And now up there we're gonna go with red. No, red bad because we have it down there. Let's use green. Right? So I'm just gonna change color. We don't have to do this time. So we're gonna call this 1, and call this 4, and say whoop, whoop, and say okay. We're going to call this the nucleon number. Okay, and just to remind ourselves, nucleon number, okay, that's great. So, we'll scratch that. Okay, and what do chemists call that number up there normally? Atomic mass or mass number. Okay, so let's use blue for that. And we're again scratching that for a specific reason. Okay, the specific reason is a couple things. Well, first of all, down here I said the reason was because we had electrons. We're going to give electrons also a number down here, and electrons are not atoms. Up here, those numbers are approximately the atomic mass, but they're not exactly the atomic mass. Okay, so what I mean by that is, for example, helium has an atomic mass of 4.0026. Yep. 4.0026 U, and where U is an atomic mass unit. So this is about 4. The chemists are very imprecise people, so that's why they're okay with that. kidding, I like chemists, kind of. Yeah, it's rounding to 4, but it's not exactly 4. Hi, how's it going there?
Good.
Good, excellente pulpante. Alrighty, Ada, you're up.
Wait, so what do I do? You just go to your.
You gotta get your locker, clear it out. You gotta label that thing, the jigger there, and then put it. You guys have done this before, right? You do this every year, no?
Yeah, but that was.
But usually we all just have a time and we'll just go.
Oh, you all go together and then you hang out in the lockers and reminisce, and that's the end of the school year, and it's good times,
Yeah.
not like this.
Yeah.
Yeah, those are the days.
How many weeks of school do we have left? Like, I've lost track.
You're counting.
7, I think. Yeah, July 2nd. Dürfen. Kaffee, come on, baby. Dürfen. Die haben jetzt unsere Einstellung geändert. Wir freuen uns, wenn wir in die Schule
But
dürfen.
I thought we only have.
Oh, wir
the
müssen ja
second
nicht.
time.
I don't know. I don't know the exact schedule. I think we're not gonna do this a lot. So I think they're trying to get everybody back at least 2, maybe 3 times or something. But they haven't made the schedule till the end of the school year yet, so that's good.
Diese Woche und in 2 Wochen brauchen wir 2
Yeah.
Cool, Dankeschön. Excellent. I should check that off. No, I'm not. Let's do it. Okay,
What's
So-
that behind the 2-6?
That's
okay, cool. That is, U
Okay.
is an atomic mass unit, and it's about 1.66 times 10 to the minus 27 kilos. And let's see if I have it more precise. Yeah, that's good. It's close enough. So it's something like that. So that's what that is. So we use because it's so much easier to talk about. Okay, so saying helium has a mass of 4.0026 is easy to understand. Saying it has like some 6 point something times 10 to the minus 27 is hard for us to picture because we're bad at small numbers. We're bad at small numbers and we're bad at big numbers. Okay, cool, great. So we're going to use those 2 labels. So if we look at our graph, okay, that was prepared by some chemist, obviously. Yeah, you guys agree? Because on the bottom, yeah, they got atomic mass number, right? As the x-axis, not really the x-axis. So what should we label that?
the nucleon number.
Nucleon number, I agree. So they have atomic mass number, and we're going to deface a scientific document. Okay, it's okay. So just scratch that and say, dudes, hello. This is nucleon number down here, right? So we can just change that. That's totally fine.
Science.
Yay, science. And on the vertical thing, they have a label that says average binding energy per nucleon. What the hell is that? Do you guys know what that is? No. Yeah, I don't either.
Aaron kennt's bestimmt.
Average binding energy per nucleon. Yeah. I'm not quite sure. That doesn't make any sense to me. I'm kidding, it does make sense, but I'm going to use different language for you guys to make it a little easier to understand. When we looked at this equation, we had hydrogen turning into helium. Could we just make 1 hydrogen into 1 helium?
No.
No, we can't do that, right? Right? Because we needed to make sure that what's conserved in this? Nucleon number, charge, or both? Both needs to be conserved. Okay? So in order to get that conserved, we gotta say, 1 here, 4 here. So we should put on the left side a 4. That's right. So now we've got good times here for the nucleon number. How about our situation with the charge number? Was that bad? We have +4 +2, right? So we got to add on the left side 2 electrons. And then we have that equation we had before. 2 electrons plus that, and then we're good to go. Because now, and we did this in class on Zoom, okay? So that's cool. So we have that situation here, and then we say, okay, now this plus this equals this. But we said there's something else coming out of this reaction. What's that other thing coming out of this reaction? Energy, exactly. So this is the trick here. There's energy. Ooh, color. We could red. Yes, red. Yes, good. Okay, so there's energy, right? And for this energy, we can use the most famous equation in the history of science. Do you guys agree? I think that's the most famous equation in the history of science. E equals delta mc squared.
But they always leave the delta out. Like,
Guy,
even
that's
in the-
true.
In the physics book.
They do. It's a little sloppy. Okay, I don't think that's the
What
first word.
exactly is the delta for?
It means there's a mass difference or mass defect. Delta M is officially called the mass defect, or we can call it the difference.
So is it the mass difference between the and the product?
Exactly. So on the left side, we looked at this way. We said, you know, we have our 4 hydrogens, right? And we said, I brought my prop here. So we mass it, right? Then we said we mass it again after we stick it together. And we find that the helium has less mass. So mass has disappeared out of the universe. It's a real thing. Mass goes away. So as the mass disappears, the mass defect, that difference in mass, is released as energy. Okay, we can actually see that on this graph. Okay, and it'll make more sense when we relabel the y-axis, but I'll show you. Take a look at hydrogen. Can you find hydrogen 1 on this graph?
Yeah.
Yeah, it's the first thing right there, right? Okay, can you guys find helium 4? Hola. Sehr gut.
Yeah.
Yeah, right? It's moved over downwards, right? And it's kind of in the hole there. You see that? The labels, the numbers don't matter as much. Rafa, you're up. Rafi?
Muss der Mann gehen und einzupacken.
Da bei diesem Desk, wo die Lady saß, da,
Bitte schön.
Hä?
da bist du nicht da reingekommen.
Nee, nee,
Da
ich
die
von vorne.
Werkstatt hat.
Die Frau vorne hat gesagt, ich darf unten durchgehen.
Wow, you're special. We know that. He is special. Okay, gut. Also, was passiert ist, Wasserstoff ist hier oben und Helium ist hier unten. Oh, we're speaking English, sorry. So, we got hydrogen and then helium is down here. It drops down, okay? So it drops down. Well, it also drops down here because this thing had more mass and this has less mass. Okay, so we're going to relabel the y-axis, okay, from average binding energy over here. We're going to relabel to average mass per nucleon. Ah, okay, so that means when hydrogen turns into helium, hydrogen on average has more mass per particle than helium. So that means when hydrogen turns into helium, those 4 nucleons that were hanging out by themselves, right, the 4 protons, are now 4 nucleons that are hanging out together. They have less mass now, and that means it's gone down on the graph. And because it's gone down on the graph, it's lost mass and can release energy. Yes,
Then why does it go up at the end again?
we're getting there.
Is that how nuclear reactors work?
Yime. So we're getting to that. Actually, her question and your question are tied together. Okay? Because you said nuclear reactor, and you meant the nuclear reactors that we are able to use,
Right.
because those are fission reactors. Okay,
Well, this is what the sun does, right?
this is what the sun does. This is fusion. So when we're looking at fusion, this is kind of, I'm going to kind of simplify a little bit. It kind of looks like this, and it comes like going up like that, yes? And then it kind of goes down like this. Is that too simple?
No.
Is that good? And here's hydrogen. Here's helium. And here's like heavier stuff. And then here's like nickel or iron or something like that. And then it's like the very heavy stuff over here. Does it agree? So the dip's somewhere around iron. They even say that. And then there's stuff heavier than iron. Okay? Yeah.
What does it say over there in the corner?
Over here?
Mass.
It says delta M equals mass defect
Oh,
or mass difference.
okay.
Okay? Cool. So, coming back to the 2 questions. So, hydrogen can turn into helium, and the overall mass has reduced because the mass per nucleon has become smaller, and because nucleon number is conserved, okay, This is a measure of like a release of energy. If the average mass per nucleon dips, then you're releasing energy. Make sense? Good, cool. So we can turn hydrogen to helium, we release energy. They've got some other stuff labeled for us here. You see that? They got also labeled for us carbon. And then they got oxygen. I'm going to be simplistic here. You see that on the diagram? Yeah, so O16. So this is carbon, helium 4, carbon 12, and oxygen 16. Yeah? So let me ask you this question. Just a second ago, we said when we take the 5 hydrogens, we combine them into helium, releases energy. Do you guys agree? Okay. Well, how about if we now say we got 3 heliums, and we're going to combine them together into a carbon. Right? That makes sense? We could do that. So this is now 4. This is a helium, helium, helium. We combine them together. Now we have carbon. Does that release energy?
Yeah.
Why do we know that releases energy from the graph? Yes?
It loses mass.
It loses mass, so it's gone down. Now, relatively speaking, does it lose as much mass as when you turn hydrogen into helium, or just a itsy bitsy bit? Yes? Itsy bitsy bit, but it still releases energy, agreed? Now, how about if we're going to take carbon and helium, and we're going to stick it together and make oxygen. Hi, gute Arbeit. Yeah? So 12, 16. Yeah? Does that release energy?
Yeah.
Yeah, it does. Because it's going down again, right? So carbon can turn into oxygen, and we're losing mass, so we're releasing energy. So you can do that too. Now we're going to go just approximately. Iron is 56, right? And oxygen is 16. So this is not exactly right, okay? But now we're going to pretend that this is oxygen, 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 so like that's 48, not quite right, right? But it's close. So pretend that 3 oxygens together make an iron. Could we make iron from oxygen and release energy?
Yeah.
Yes, right? Because again, if you look at the graph, it's lower down. So iron is dropping down again. That makes sense so far? Now, let me ask you this. If you have iron, so here's our iron particle, and you try to add something to iron, will that release energy then anymore?
No, it takes energy.
It takes energy. Okay? So if you look at this graph, not quite simplistic, but it's pretty much saying that along this area, fusion, oh shit, we need to send somebody else out, right?
Oh.
Yes, that's fine, totally good. Yeah, forgot about that. So here's your little tag. There you go. And along this area here, fusion releases energy. Okay? So fusing hydrogen into helium releases energy. Fusing helium into carbon releases energy. Fusing carbon into oxygen releases energy. And into silicon. And then into iron, that's always releasing energy. Make sense? So all along here, releases energy. What's another word for that from chemistry, by the way? Starts with exo, ends with thermic.
Oh, okay.
Exothermic. You guys are really good. You guys are so good. Excellent. Okay. So it's the same thing. This thing means exothermic. So now, just a reminder about that. Can only exothermic reactions happen, or can we also make reactions happen that are the other thing? What's the other thing again? Endothermic. Okay, so endothermic works too, but what do we need to do to make them happen? Add energy. We shove energy into the situation and we can make endothermic reactions happen. So we could take, for example, oxygen and break it apart into helium, right? but that would require energy. It wouldn't release energy, it would require energy. So turning oxygen to helium would require energy. Cracking apart a helium nucleus and turning it into hydrogen also requires actually a lot of energy, right? But you could do it. Make sense? Now coming back to your question and your question combined, together they made sense, but now I lost track of exactly what you guys asked. Either way, if we think about it, okay, that's cool, but then it goes back up over here. So that means fusing iron into anything else is endothermic. Of course, on the other hand, going this way is endothermic, but over here going this way, so for example, let's say, do they have stuff labeled on there? Oh, they do! Sorry, I got a little excited. Okay, so we got over here, this is uranium, 238, and uranium you're probably familiar with, right?
Yes.
Yeah. We use uranium in what?
Nuclear reactor.
Nuclear reactors. So when you have uranium, and you take that uranium, okay, and you break something off, like a helium particle, or something else, or you just take the whole thing and you crack it in two. It's scooching this way, right? That means uranium and other elements over here have a tendency to release energy if they go to the left. So on this part of the graph, we call that fission. Releases energy. So over here, if we take uranium and crack it apart, make it into something smaller, we can release energy. Now, let me ask you this question. Using this graph, can you tell me whether hydrogen fusion or uranium fission is a more energy efficient process, releases more energy?
Uranium fission, fusion.
Okay, just think about it for a second. Looking at the graph, okay, so the question is,
Oh no,
hang on a second, just think about it for a second. Okay, so, is hydrogen fusion or uranium fission more energy efficient? Justified.
Meaning like, releases more energy.
Yeah, I think that's what we mean. Yeah, exactly. So release more energy. So let's call on somebody else. Besides the people who always participate. Kathy, what's up? Am I coming in and out of the screen now?
What?
It's kind of weird. Yeah, good. Go.
I'm just gonna guess maybe because everyone said hydrogen fusion.
Coffee's like, it's a 50-50, man. My whole school career is built on 50-50s. Okay, Coffee. We're going to help you think a little bit. Okay. When hydrogen turns to helium, how do we see in the graph that that releases energy? Just look at the graph. You can look there or there.
And
Hydrogen is here. This is hydrogen. And here's helium. And on the graph, we know that hydrogen releases energy when it turns to helium, because on the graph, what happens to the mass? Wird weniger, becomes smaller, wird kleiner. Okay? So the energy release is due to the reduction in the mass, the difference in the mass. Now, how about uranium? When uranium fissions to something over here, from there, I don't even know what it turns into. It goes from there to there. Does it also release energy? Going from here to there? Yeah. Why do we know that it does?
Oh, dachte, wenn es andersrum ist, dann.
Nee, guck mal drauf. Wird die Masse kleiner? Von Uranium zu, weiß ich nicht, Lead. Ist auch egal. Genau.
Ach so, ja, ich dachte, das ist anders.
Ist alles okay, Raffi, verstehst du?
Ja.
Die Masse wird kleiner. Jetzt guck mal hier, Uran, ja, Blei, hier drüben Wasserstoff und Helium. Okay? Welches fällt weiter runter? Wasserstoff zu Helium. Der Massenunterschied ist viel größer. Okay? Also, turning hydrogen to helium releases more energy than turning uranium and lead. I'm not even sure that's it, but whatever it is, right? So uranium this way, all this stuff, if you look at this, there's not even if it dropped all the way to iron, this is not a big drop. You can see that on the graph, right? It's like really, it's kind of flat, right? I mean, going down this way, but it's not a big difference. So any of these fission reactions over here are much less efficient at releasing energy than turning hydrogen into helium. Make sense? Okay, so that means, dude, here's where the big bucks are. That's not just about money, but also in terms of energy sufficiency. If we were able to harness the power of hydrogen fusion into helium, we'd be like rolling in energy. Tremendous amounts. Because this is already, actually, apart from concerns regarding us all dying in a Fukushima explosion or Chernobyl or whatever, right? Energy efficient enough to make money on it. And actually, nuclear power plants work, right? They release energy and also radioactivity, so that's kind of a worry of us. But over here, this would release much more energy, plus, what's the side product? What do you get when you turn hydrogen into helium? Trick question. Helium! Is helium a bad thing?
No. So it's not
It's-
like nuclear.
Not just not a bad thing, it's awesome! Right? Helium? You can make birthday balloons, right? You can make